The Argand diagram. Just as a real number can be represented on a real number line, a complex number can be represented on a diagram called the Argand diagram, also known as the complex plane. The Argand diagram is a two-dimensional plane with two perpendicular axes. The horizontal axis is the real axis, so we would be used to calling this the x-axis, and the vertical axis is the imaginary axis. So we would be used to calling this the y-axis. But we only use x and y for coordinate geometry. Now we are using complex numbers. So the horizontal line is the real axis and the vertical line is the imaginary axis. Here is the complex number 3 plus 2i represented on an Argand diagram. So 3 has no I stuck onto it, so that must be the real part. So we go across our real axis to 3. And the 2 has an I stuck onto it, so that's the imaginary part. So we go up our imaginary axis to 2. So 3 on the real axis, 2 on the imaginary axis, and we plot our point. So this point right here is the complex number 3 plus 2i. So the real axis can have the letter or the letter I, or the real axis can be labelled as RE, and the imaginary axis as IM or I. So this represents the same thing, 3 plus 2i. Represent the following numbers on an Argand diagram. Part 1. So we have minus 1 plus 2i. So minus 1 is the real part, so we go across on the real axis to minus 1. And 2i is the imaginary part, we go up our imaginary axis to 2, and we plot our point. So this point right here is minus 1 plus 2i. Next we have 2 plus 3i. So the 2 is the real part and the 3 is the imaginary part. So we go to 2 on the real axis, which is here, and we go to 3 on the imaginary axis, which is here, and that is where we plot our point. So this point here is the complex number 2 plus 3i. Next we have minus 3 minus 2i. So minus 3 is the real part, so we go across to minus 3 on the real axis. And minus 2 is the imaginary part, we go down to minus 2 on the imaginary part. So minus 3 minus 2i, so that is the point there. That is the complex number minus 3 minus 2i. Next we have 3 minus I. And I is really 1i, so this is actually minus 1i. So we go to 3 on the real axis and minus 1i on the imaginary axis. So 3 on the real axis is here, and minus 1i or minus I on the imaginary axis is here. So 3 minus I is here. This point here is the complex number 3 minus I. The modulus of a complex number a plus bi is its distance from the origin, so the centre 0, 0. So the modulus of a complex number is the distance from the origin. This is very important to learn off. So z1 is equal to 12 plus 16i, and z2 is equal to minus 12 plus 5i. We want to find the modulus of z1. So these two lines, we are used to calling them distance or length, but now in this chapter complex numbers, they represent modulus. So the modulus of the complex number. So the formula for modulus is the square root of a squared plus b squared, where a represents the real part and b represents the imaginary part. So let's start with z1. So 12 is the a and 16 is the b. So we're going to have the square root of a squared, which is going to be 12 squared, plus b squared, which is going to be 16 squared. So we do not use I in the square root, we forget about the I. 12 squared is 144, 16 squared is 256, adding them we get 400, and the square root of 400 is 20. So the modulus of z1, or the distance from z1 to the origin, is 20 units. Part 2, find the modulus of z2. So z2 is minus 12 plus 5i. So the modulus formula is the square root of a squared plus b squared, where a represents the real part, which in this case is minus 12, And b represents the imaginary part, which in this case is 5. Remember, we dropped the I, we just use 5. So we have the square root of a squared, which is going to be minus 12 squared. Make sure you use brackets around the minus 12, plus b squared, which is going to be 5 squared. Remember, it's not 5i squared, it's just 5 squared. Minus 12 squared is 144, 5 squared is 25. Adding them, we get 169, and the square root of 169 is 13. So the modulus of z2, or the distance from z2 to the origin, is 13 units. We should never have a negative number in here for modulus, because if this is a negative number, a minus by minus will always give us a plus. So we should always have a positive number in here when we're coming up with the modulus. And that makes sense because modulus is the distance from that complex number to the origin, and distance or length can never ever be negative. You don't say your hair is minus 20 centimeters long. You don't say you walked minus 2 kilometers to the shop. Distance and length must always be positive, and modulus must always be positive. Part 3. Work out the modulus of z1 plus z2. So since the modulus symbol is outside of z1 plus z2, we're going to work what's inside the modulus symbol first. So we're going to add z1 plus z2. So z1 is 12 plus 16i, and z2 is minus 12 plus 5i. Now the rule for adding or subtracting complex numbers is we add the real with the real and the imaginary with the imaginary. So 12 is the real part in z1, and for z2, minus 12 is the real part. And 16i is the imaginary part for z1, and plus 5i is the imaginary part for z2. So we're going to have 12 plus 16i plus minus 12 plus 5i. So we're going to add the real with the real. 12 plus minus 12. So 12 plus minus 12 will just cancel and give us 0, because 12 take by 12 is 0. And then the imaginary with the imaginary, so 16i plus 5i. So 16i plus 5i is 21i. So next we're going to get the modulus of 0 plus 21i. So the formula for modulus is the square root of a squared plus b squared, where the a represents the real part, which in this case is 0, and the b represents the imaginary part, which in this case is 21. So we get the square root of a squared, which is going to be 0 squared, plus b squared, which is going to be 21 squared. Remember, we ignore the I for the modulus. 0 squared is 0, 21 squared is 441. Adding them, we get 441. And the square root of 441 is 21. So the modulus of z1 plus z2 is 21 units. Or the distance of z1 plus z2 from the origin is 21 units. Part 4. Hence, show that the modulus of z1 plus z2 is less than the modulus of z1 plus the modulus of z2. So the modulus of z1 we worked out in part 1. And we got the modulus of z1 to be 20. So the modulus of z1 is 20. We worked out the modulus of z2 to be 13. So in part 2, we worked out the modulus of z2 to be 13. So the modulus of z2 is 13, and 20 plus 13 is 33. So the modulus of z1 plus the modulus of z2 is 33. In part 3, we worked out the modulus of z1 plus z2 to be 21. So in part 3, we got the modulus of z1 plus z2 to be 21. So the modulus of z1 plus z2 is 21. And since 21 is less than 33, the modulus of z1 plus z2 must be less than the modulus of z1 plus the modulus of z2. So this seems like quite a tricky question, but if you work out each of the parts separately, which we did, and then add together the modulus of z1 and the modulus of z2, we can see that 21 is less than 33. z1 equals 8 minus I and z2 equals 7 plus ki are two complex numbers. Find the modulus of z1. So again, we use our modulus formula. And our formula is the square root of a squared plus b squared, where a represents the real part and b represents the imaginary part. So for z1, a is 8 and b is minus 1, or in this case minus 1i. But when we substitute our values into our formula, we ignore the I. So we get the square root of a squared, which is 8 squared, plus b squared, which is minus 1 squared. 8 squared is 64, minus 1 squared is 1, because minus 1 by minus 1 is 1. And 64 plus 1 is 65. So the modulus of z1 is the square root of 65. So the distance from z1 to the origin is the square root of 65. Part 2. Find the modulus of z2 in terms of k. So in terms of k just means k needs to be in your answer. So again, our modulus formula is the square root of a squared plus b squared, where a is the real part and b is the imaginary part. So for z2, 7 is the real part and k is the imaginary part. Remember, we ignore the I, but we keep the k. So we substitute into our formula. So we have the square root. A squared is going to be 7 squared plus b squared is going to be k squared. So we ignore the I and we keep the k. So we've got k squared. Then we simplify as much as we can. 7 squared is 49 and k squared just stays as k squared. So we cannot simplify anymore because k is an unknown value. So the modulus of z2 is the square root of 49 plus k squared. Part 3. If the modulus of z1 is equal to the modulus of z2, find the two possible values for k. So we're going to try and solve for k. So if the modulus of z1 is equal to modulus of z2, then the square root of 65 is equal to the square root of 49 plus k squared. Because in part 1, we worked out that the modulus of z1 was the square root of 65. And in part 2, we worked out that the modulus of z2 was the square root of 49 plus k squared. So we just let them equal each other, and then we solve for k. So notice that we have a square root on both sides. So we want to start by getting rid of the square root. So what we do is we're going to square both sides. So remember, with solving, what we do to the left, we do to the right. So squaring the square root of 65, the squared and the square root will cancel and just leave us with 65. The square root of 65 squared is just 65. The square root and the squared will cancel. And likewise on the right, the square root of 49 plus k squared squared, the square root and the squared will cancel and just leave us with what is underneath the square root, which is 49 plus k squared. So we want to get this k on its own. So we start by getting rid of the 49. We bring the 49 over the equal sign, it becomes minus 49. So we have 65 minus 49, which is 16. So 16 is equal to k squared. So now we want to solve for k, we want to get the k on its own. So we're going to bring the squared over the equal sign and it becomes square root. And the square root of 16 is plus or minus 4. And the square root of 16 is plus or minus 4. Because 4 squared will give us 16, 4 multiplied by 4 is 16, and minus 4 squared will also give us 16. Minus 4 multiplied by minus 4 is positive 16. So both of these answers are correct, so these are the two possible values for k.